All right, now we have lesson 5.5, which is on the roots of real numbers. And the big thing to remember here is that all of these are going to be real numbers. In 5.9, we're going to be talking about complex numbers, and complex numbers will change things up a little bit, and I'll point out where the changes are going to be. But for right now, just remember and realize that we are working only with real numbers here. Now, first thing we're given is a chart of different numbers, or n, and their different exponents. So here we can see we have where n is 2. If we had n squared then, that would be 4, or n to the third power would be 8, n to the fourth 16, all the way across to, some of them even go as high as n to the sixth. Now, all of these are going to be very, very helpful when we're looking at the roots of numbers. Now, if we think about the squaring or the rooting of a number as being an operation, n squared is basically n times n, and that would be an operation basically. It's taking that number and multiplying it by itself. So just like how multiplying has an inverse operation, so say we had 3 times 4 equals 12, then the inverse operation would be 12 divided by 4 would get us right back to 3 that we started with. Well, if say we started with 2 cubed, according to our chart, gives us 8. There's also an inverse of that. So just like here, how we got to 12 by taking 3 times 4, and then we started at 12 here and went 12 divided by 4 here to get back to our 3. In this case over here, we can take the cubic root of 8, and that'll get us back to 2 where we started. So that's what's called the inverse operation. So the inverse of cubing a number would be taking the cubic root. Similarly, we have squaring. The inverse would be the square root. So this table will be very useful for looking at, okay, if I have a number like 81 and I want to know the fourth root of 81, I know that it's going to be 3. And that's because 3 to the fourth is 81. So you can use this chart. In fact, if you look on your blue sheet, this chart is even on your blue sheet. So you can use this chart for your homework, your quizzes, and your tests to help you find differing amounts of roots. And we're actually just going to look at a couple different examples where this is going to come into play. Now, again, first thing we want to look at is this radical sign, or this root. It always means to a certain power, but going the inverse direction. If it doesn't have anything out front here, if there's nothing there, just know that it implies the square root. Okay, so if it's just a radical, it's a square root function instead of, like, it could be a cube root or a fourth root, but if it doesn't say anything, it is a square root. So that's one thing to remember. Another thing to remember is if we are squaring something, so say I have 2 squared, that's going to be 4. But if I have negative 2 squared, negative 2 times negative 2, that's also 4. Similarly, if I do 2 to the fourth power, if we look at our table, 2 to the fourth power is going to give us 16. But also negative 2 to the fourth power gives us 16. So these, the 2 and the 4, the roots that we're going up to, those are all even. So whenever you have an even root, it can be positive or negative. But if we look at an odd root, so 2 to the third power, looking at our table, 2 to the third power would be 8. But if we did negative 2 to the third power, that would be negative 2 times negative 2 times negative 2. This negative and this negative would essentially cancel out, make a positive. But then this last negative here keeps it negative. So in this case, it would be a negative 8. So they're not the same. So anytime that you have an odd root, so like 3, 5, 7, 9, those ones are only the same sign as what you have. And those will come up. I'll show you one example that specifically looks at how that one works. So if we look at our first example here, we have example A is the positive and negative square root of 16 times x to the 6th. Now again, remember this square root, the radical, is over everything here, so 16x to the 6th. So ways that we can look at that is, again, remember that it's our square root, or our 2. One easy way that I know to do that one is to view this as 4 squared is 16, and going exponent to exponent, inside here is going to be x cubed to the 2nd power. So this is another way to rewrite 16x to the 6th. And we're taking the square root, and I guess I could even add that it's positive and negative. Now that we have it in this form, our square root and our 4 squared and x cubed squared, the radical and the squared exponents all essentially cancel each other, leaving us with 4x cubed, which I guess we could just write as 4x cubed. So that's one way to look at it. Another way, if we wanted to look at it this way, we would say that 16x to the 6th is the same as saying 4 times 4 times x times x times x. It's 3, 4, 5, 6. Here we have 2 of them. Here we have 2, here we have 2, and here we have 2. And out of each of those groups of 2, we only need 1 because we're doing the square root. And that leaves us with 4 and x to the 1, 2, 3. So either way, we come up with that 4x cubed. So they're both valid ways to look at it or to get the same answer. One just might take a little longer than the other one might. So that would be our first example. Moving on, looking at our second one here. This one specifically is asking us for only the negative version. So we have the negative square root of, and again, this one is a polynomial, or technically a binomial, of q cubed plus 5 to the 4th power. Now again, one way to look at that is to say that we have q cubed plus 5, and we have that 4 times. So we'll just say that there's 1 here, 1 here, 1 here, and 1 here. So q cubed plus 5, q cubed plus 5, and q cubed plus 5. These are all being multiplied together. Again, we put them in groups of 2 because this is the square root. So here's a group and here's a group. Out of each of these groups, we only need 1 of them. And so that just leaves us with q cubed plus 5 times a q cubed plus 5. Or we can rewrite that as q cubed plus 5 squared. That would be one way to look at it. Another way to look at what we have here, oh, and again, we have to remember that it's the negative, so we put the negative sign on the outside. Another way to look at this one would be to notice that if we have a square root and what we have on the inside is going to the 4th root, we can just divide out our 2 from our 4, in which case we are then left, again, with the negative first, q cubed plus 5, and instead of to the 4, it would be to the 4 over 2, or 4 divided by 2, which is just to this 2, or squared. Again, 2 valid ways to get to the same answer. Both are correct. So if we apply similar properties to our third example here, C, again, we have the 5th root of 243 times a to the 10th times b to the 15th. Now again, we're looking at everything in terms of 5, or the 5th root. So first thing we want to do is notice that 243 is the same as saying, oops, I'm going to use, I'll go back to black here. That's the same as 3 to the 5th power, because according to our table, 243 equals 3 to the 5th. So we'll just rewrite it. Oops, I want to erase that one. We'll rewrite it as 3 to the 5th. A to the 5th, or to the 10th, well, that would be the same as saying a squared to the 5th. Because remember, anytime that we have a exponent to an exponent, you multiply them. So 2 times 5 is 10. And looking at our b to the 15th, in a similar way, that would be b cubed, or b to the 3rd power, to the 5th, because 3 times 5 is 15. Now that we have it in this form, again, we still need to recognize that it is the 5th root. Well, just like we did before, we would cross out all of our 5th roots, and we would just be left with 3a squared b cubed. And this one would be our final answer. And again, because it is an odd root, we only use the sign that we have. And since it didn't have one out front, it's assumed that it's positive and not a negative. Sorry if that looked like positive, negative. It's just the positive version. So we know that this is going to be our answer.